Hey everyone, welcome to This Explainer. Today we're diving into something literally invisible but absolutely crucial to how our modern world works. We're talking about the magnetic effects of electric current. If you're gearing up for your 10th grade science exams, well, consider this your ultimate plain English study guide. We're going to demystify these invisible forces and make the whole thing super easy to understand.
Okay, so here's our game plan. We'll start with the underlying connection between electricity and magnetism, learn how to actually map out a magnetic field, master those tricky hand rules, figure out how motors and generators do their thing, and finally, look at how all this applies to keeping your home circuits safe.
All right, kicking things off with part one, the connection between electricity and magnetism. And it actually all starts with a total accident.
Picture this. You're observing physicist Hans Christian Ørsted's famous experiment. He's got a regular compass sitting near a metallic wire. Normally, a compass just points north, right? But the absolute second an electric current travels through that wire, the compass needle suddenly deflects. This was a mind-blowing realization. It proved that moving electrical charges actually generate a hidden magnetic field right there in the surrounding space.
So, here's the massive takeaway. Permanent magnets? They aren't the only source of magnetism out there. Electric current itself is a powerful magnetic source. Whenever electricity flows, magnetism is born. They aren't just related, they're literally two sides of the exact same invisible force.
Moving right along to part two, mapping the magnetic field. Now that we know this invisible force exists around wires, how do we actually visualize it?
Think about a classic bar magnet. Its magnetic influence extends outward into the surrounding area, which, by the way, we measure in a unit called Teslas. We use field lines to basically draw a map of the magnetic force's direction and strength.
Now for your exams, you absolutely have to nail these properties. The field lines always emerge from the North Pole and curve right around to the South Pole, forming continuous closed loops. Notice how they bunch up and get super dense near the poles? That tells us the field is strongest right there. And here is the most crucial rule. Field lines never, ever intersect. Seriously, no crossing. Why? Because if they did, a compass placed at that intersection would have to point in two different directions at the exact same time, which is obviously impossible.
Okay, so what happens if we take a straight, current-carrying wire and bend it into a circular loop? Well, the magnetic field lines form these perfect, concentric circles. Depending on the current's direction, the field emerges from the inside of the loop and loops back downward on the outside. It's a beautifully structured pattern.
Let's take that idea one step further. If you stack a bunch of those circular loops together into a tightly wound cylinder, you get what's called a solenoid. Inside that coil, the field lines are perfectly parallel and straight. That indicates a really strong, uniform magnetic field that mimics a traditional bar magnet flawlessly, complete with its very own north and south poles. So how does an electromagnet stack up against a regular permanent magnet? Well, a permanent magnet has a fixed polarity and is relatively weak. But if we drop a soft iron core inside that solenoid coil we just talked about, boom, you've got an electromagnet. It's temporary, meaning you can just switch it off. It's way stronger, and you can even instantly flip its north and south poles just by reversing the electric current. Talk about a game changer. All right, let's tackle part three, mastering the hand rules. To predict how these invisible forces behave, especially on a test, you need to master what I like to call the physical cheat codes of physics.
First up is the right-hand thumb rule, also known as Maxwell's corkscrew rule. This is your go-to tool for figuring out the direction of the magnetic field around a straight wire.
Seriously, try it with me right now. Hold out your right hand. Pretend you're grabbing the wire, point your thumb in the exact direction the current is flowing. See how your fingers naturally curl inward? Those curled fingers perfectly represent the concentric, circular field lines wrapping around the conductor. Super simple, right?
Next on the docket is Fleming's left-hand rule. We learned from the French scientist Ampere that when you place a current-carrying wire inside an external magnetic field, the two magnetic forces kind of duke it out. They interact and create an actual physical push, or motion. Fleming's rule predicts exactly which way that push is going to happen.
Okay, whip out your left hand for this one. Stretch your thumb, your forefinger, and your middle finger out so they're all perpendicular to each other, kind of like the corner of a room. Your forefinger points to the magnetic field, your middle finger points to the current, your thumb then reveals the direction of the force or motion. Master this little trick and you've literally unlocked the secret to how electric motors spin.
And speaking of spinning things, let's jump to part four, motors and generators. Let's see how these basic rules scale up to the massive machines that power our world.
Let's break down a basic electric motor. Its whole job is transforming electrical energy into mechanical energy. Using that left-hand rule we just practiced, imagine current flowing through a rectangular coil sitting between a north and south magnet. The interaction creates an upward force on one side and a downward force on the other. This makes the entire coil spin. It's the exact same tech coming away inside your electric fans and washing machines.
But wait, there's a slight catch. After just a half spin, the coil would naturally get stuck flipping back and forth. The absolute genius fix for this is this split-ring commutator. It acts as a mechanical switch that flips the current direction inside the coil every single half turn. This guarantees the force keeps pushing in the same direction, letting the motor spin continuously without jamming up.
Now let's totally flip the script. The AC generator does the exact opposite. It converts mechanical energy back into electrical energy. This relies on a process called electromagnetic induction, which Faraday discovered. By mechanically spinning a coil inside a magnetic field, we actively force an electric current to flow through the wire. Literally, this is how massive power plants generate the electricity for entire cities.
You definitely need to know the difference between the two types of current. Direct current, or DC, just flows in one steady direction, like what you get from a battery. Alternating current, or AC, comes from generators that use slip rings to reverse the current's direction periodically. AC is the stuff coming out of your wall sockets, mainly because we can easily step up its voltage using transformers, making it incredibly cheap and efficient to transmit over long distances without losing energy to heat.
Which brings us perfectly to our final section, keeping your home safe. Let's bring all this high-level physics right into your living room and see how domestic circuits actually manage this 220-volt AC power without burning the house down. Your home setup relies on three very specific insulated wires working together. The live wire, usually brown or red, brings the current in at a spicy 220 volts. The neutral wire, light blue or black, returns the current to complete the circuit at zero potential. And finally, the earth wire, green or yellow, is your ultimate safety net. Your home's appliances are wired in parallel across the live and neutral wires. That parallel setup is why your TV and your kitchen lights can operate totally independently, each getting their full 220 volts.
Now, because we're dealing with serious electrical and magnetic power here, things can absolutely go wrong. Overloading happens when too many appliances try to draw excess current at once. A short circuit, that's when your live and neutral wires accidentally touch.
Yikes.
Thankfully, physics gives us built-in safety nets. An electric fuse has a wire with a super low melting point. If the current spikes dangerously high, the wire simply melts and breaks the circuit. And that green earth wire, it connects the metal casing of your appliances deep into the literal ground. So if there's a dangerous leak, the current safely flows into the earth instead of giving you a nasty shock.
And there you go. I really hope this explainer made the whole magnetism and electricity connection crystal clear for your exams. But more than that, I hope it sparked just a bit of curiosity about the hidden mechanics making your everyday life possible. Seriously, think about it. If moving tiny invisible electrons can spin a motor, and spinning a motor can literally light up a whole city, what other invisible forces are quietly shaping your world right now? Keep questioning, keep digging into the science, and hey, best of luck on your exams.